In lecture 30 of our series on numerical methods in civil engineering, we are going to talk about interpolation. In the previous lecture, I talked about various difference operators, and I said how you can approximate various differential expressions which appear in the partial differential equations which commonly occur in civil engineering, and we saw how we can use difference expressions to approximate those differential operators. And one of the particular differential operators that we talked about was the Laplacian operator, which, as we saw earlier, occurs in almost all the major equations of interest, partial differential equations of interest in civil engineering, the wave equation, the diffusion equation, as well as the wave equation, the diffusion equation, as well as the heat equation. So, the Laplacian operators that we talked about was the first operator, which is on the left hand side, which is centered, and the other operator that we talked about was the diagonal Laplacian operator. And I also mentioned that you can construct a composite operator by using by weighing each of these different approximations to the Laplacian operator to come up with a composite operator. For instance, by multiplying the first operator that we saw with 4 and adding to that the second operator, we get this operator, and you can see this is 6/8 square times Laplacian, right. So, as I told you that it is always better to add them together and then divide it by 6 to get the Laplacian operator, rather than dividing it, because that is going to accumulate round off, right. Okay, and we also looked at how we can. So, we looked at the Laplacian operator on a rectangular grid, how we can approximate the Laplacian operator in a rectangular grid, and we also looked at how we can approximate the Laplacian operator on a regular triangular grid. For instance, I have a triangular grid like this with each triangle of side h, right, side h, and if I want to find out what is the Laplacian at this point x within a triangle, how can I use my difference expressions to find an expression for the Laplacian at this point? We saw that, right. But when it comes to irregular triangular grids, that becomes a problem, as I mentioned, it is in real world problems, it is almost always the case that the grid is irregular. First of all, because the first reason being the geometry is irregular, number one, and number two, the reason why we want to use triangular grids is because we want to do free meshing, right. In a particular region, if we have sharp gradients, we would like to have a finer mesh in that region, right. So, in that case, it is inevitable that we are going to end up with irregular triangular grids. So, what does the Laplacian operator look like when we consider an irregular triangular grid? For a regular triangular grid, the Laplacian at an arbitrary point x located within the triangle, as we saw, is the weighted sum of the Laplacians calculated at the 3 vertices of the triangles, right. So, in order to find the Laplacian at this point, right, what we did was that we formed the Laplacian here, we formed the Laplacian here, and we formed the Laplacian here, and then we use the barycentric coordinate of this point, the triangular coordinate of this point, to weigh the Laplacians evaluated at each of those points to find out the value of the Laplacian at this point. Instead of considering a regular triangular mesh, we want to consider an irregular mesh, right, and the irregular mesh that we are going to look at is a very simple irregular mesh, in that it differs from a regular mesh by only a small perturbation. But if conceptually we understand how we evaluate the Laplacian operator at such an irregular mesh, we can extend the idea to arbitrary irregular meshes. So, the irregular mesh we will consider is something like this, where it is very similar to the previous mesh, except that you can see the orientation of these two triangles is different from the rest of the triangles, right. So, we have changed the orientation of these two triangles, but kept the orientation of the rest of the triangles the same. So, two triangles are different. So, if we recall this RU x h plus y, we encountered that in our previous lecture, that is the interpolant, right. It is the interpolated value of u evaluated at x plus hy. What is x plus hy? Well, x plus h, if this is x, right, x plus h would be somewhere here, right. So, RU x plus hy, RU x minus hy, RU x y plus h are the same as earlier. Why? Let us go back and take a look. So, x plus h, the triangle, the shape of the triangle is the same, so that remains the same. X minus h, somewhere here it refers to this triangle, so that triangle is the same. X, if you look up there, right, x plus x in the y direction plus h, that triangle is also the same. So, the triangle that is different is going to be x y minus h, because that refers to this triangle, which as you can see has got a different orientation than the previous triangles, right. So, these are the same as earlier, however, this is no longer the same. If the barycentric coordinate of the point with global coordinate x, y minus h in this triangle is denoted, so what we are saying is that this is the triangle of interest, right. So, if we denote these nodes as 5, 6 and 7, then we look at x, y minus h, which lies somewhere here, right. X, y minus h is denoted by theta 5, theta 6, theta 7, then we can write the interpolated value of u at this point as theta 5 u minus 1 j plus theta 6 u minus 1 j minus 1 plus theta 7 u I j minus 1. Let us go back again and take a look. So, it is theta 5 times u I minus 1 j, right, plus theta 6 u I minus 1 j minus 1, so I minus 1 j minus 1, and this is theta 7 u I j minus 1, right. So, it is the interpolated values of all these three values, right. So, R u x y minus h is equal to theta 5 u I minus 1 j plus theta 6 u I minus 1 j minus 1 plus theta 7 u I j minus 1. So, let us go back to that figure and look at x and y, look at this point, right, with coordinates x and y. So, we can write x and y as x and y is equal to theta 1, x is actually theta 1 times 0 plus theta 2 into minus h plus theta 3 into 0. Why? Let us go back and take a look. So, if I want to find out x, it is, while this is my first point theta 1, it has got 0, x coordinate 0. This point has got x coordinate minus h, that point has got x coordinate 0. So, it is theta 1 times 0 plus theta 2 times minus h plus theta 3 into 0. Similarly, y, the y coordinate of this point is equal to theta 1 times 0 plus theta 2 times 0 plus theta 3 times h. So, that is what I have just written here, right. And if I do this, simplify this, I get minus theta 2 h, theta 3 h. That I know is the barycentric coordinate. Using the barycentric coordinate, the x y coordinates can be written like this, right. So, from here x y minus h I can write as minus theta 2 h, that part remains the same because the x coordinate is remaining the same. The y coordinate is decreased by h, so that becomes theta 3 h minus 1, so theta 3 minus 1 h. But if we consider the shaded triangle, if we consider this triangle again, right, and we look at x y minus h, then in that case that is equal to theta 5 times minus h plus theta 6 times minus h plus theta 7 into 0. It is theta 5 times minus h, theta 6 minus h, theta 7 0, right, and the y-th coordinate is equal to theta 5 into 0, theta 6 into minus h, theta 7 into minus h. So, that is what we get, and if I simplify that, that becomes minus theta 5 h minus theta 6 h minus theta 6 h minus theta 7 h. but these two have got to be equal, right. You cannot have x y minus h different depending on which triangle you use it to calculate it, right. So, these two have to be the same. So, this gives me a relation between theta 2, theta 5 and theta 6, and theta 3 minus 1 and theta 6 and theta 7. So, what do I get? I get theta 2 is equal to theta 5 plus theta 6, theta 3 is equal to 1 minus theta 6 minus theta 7, which is equal to theta 5, since all the barycentric coordinates must sum up to 1, right. And theta 1 is equal to 1 minus theta 2 minus theta 3, which pulling these two together I get theta 7 minus theta 5, right. So, now if I denote the new interpolant as I prime u of x, then Laplacian of I prime u of x using our operator which we have seen earlier can be given like this. This we have seen before, right. This we have seen before. So, this is I prime u x plus h y minus 2 I prime u x y plus I prime u x minus h y, that is in the x direction, and this is in the y direction, x y plus h, x y minus h, right. So, that remains the same. I prime u x h plus y is equal to I u x h plus y, that I already know, right. U x y, I prime u x y is equal to I u x y, I prime u x minus h y remains the same. This part remains the same as the previous interpolant. That only thing that is going to change is this one that we have seen earlier, right. So, this I can write as this, where this I calculated using my regular grid, right. I calculated using the regular grid. So, the only part that is changing is this part. So, again this is just the expression for that, right. This we have seen earlier, writing it in terms of these quantities, and now the only thing that has changed is this term, right. This term which I can write as from my previous expression, and now this one, this expression, right. I can use that expression to write this as like this, right. I can write it like this. So, this part remains the same, this is practically identical, but then what I have done is that instead of writing this, I have used the previous expression, right. I have used the previous expression, and then I have, but this plus this must be equal to that, right. This plus this must be equal to that. So, this is the previous expression which I got using my regular grid, right. This I got using my regular grid, and then I have to correct it to get that expression. So, I have to add to it this term, right. I have to add to it that term. So, this is what I got using the regular grid, right, but now I know that this term is different. So, you can see that if I subtract theta 1, theta 2 and theta 3 are going to cancel out if I add these two terms together, and I am going to get theta 5 u minus 1 j plus theta 6 u minus 1 j minus 1 plus theta 7 u I j minus 1. These three terms are going to cancel out, right. So, the advantage why I want to do this, because I want to write it as well as my previous expression, So, we can write del 2 5 I prime u of x, del 2 5 using the new interpolant is equal to del 2 5 using the old interpolant plus this correction term, right. Let us go back again. So, this is my del 2 5 using the old interpolant up to here, right, and this is my correction term, right. So, that is my correction term. So, I can write it as this is evaluated using my regular grid plus a correction term which is due to the irregularity of the grid, right. This is due to the irregularity of the grid. So, using these expressions right there which I obtained between theta 2, theta 3, theta 1 and theta 5, theta 6 and theta 7, I can write this E, this expression in like this, right. Basically, I can write everything in terms of theta phi, Why? Well, theta 5 u minus 1 j is theta 5, that remains the same. Theta 6 minus theta 2 I can write using that expression. Theta 6 minus theta 2 is minus theta 5, right. So, that gives me minus theta 5 here instead of theta 6 minus theta 2. Then I have theta 7 minus theta 1, which I can write using this expression, theta 7 minus theta 1 equal to theta 5, right. So, that I can again write as theta 5 ui j minus 1, right, and then I have theta 3, which again I can write straight away as theta 5, right. I can write straight away as theta 5. So, I can get everything in terms of theta 5 and u minus 1 j u this that. Then I pull out theta 5 and I am left with that term, right. So, my new Laplacian on the irregular grid is the old using the regular grid plus an error term, and the error term can be represented by theta 5 plus this. Now, this term, it can be shown that is actually a finite difference expression for the mixed derivative, right. Up till we are considering the Laplacian, but now you can see that when we move to an irregular grid, we also it also involves the finite difference approximations for the mixed derivative, right. So, we are evaluating the Laplacian, but since the grid is irregular, we have this additional term which is actually a finite difference approximation of the mixed derivative, right. So, this representation of the mixed derivative, is second order accurate. So, the error is also second order due to the irregular grid. Thus, we can see that the irregularity of the grid results in a finite difference formula for the Laplacian, which is near identical to the formula for the Laplacian on the regular grid, except for certain additional terms which can be shown to represent contributions from a mixed derivative, right. So, this is for a really simple irregular grid, but as you can understand, in a real irregular grid, in a general irregular grid, there will be contributions at many locations from mixed derivatives to the formula for the Laplacian, right. There will be lots of contributions from mixed derivatives, right. So, if you evaluate the Laplacian using a regular grid, you have to add additional corrections for the fact that the grid is irregular, and those correction terms will involve finite difference approximations for the mixed derivatives. So, although we are evaluating the Laplacian, right, which does not involve any mixed derivatives, right, our finite difference approximation is going to involve mixed derivatives if we have a irregular triangular grid, right. This is just to give you some idea of these operators. So, there are many complex operators and for irregular grids, but the fundamental principles are the same. So, we have looked at finite difference operators for a rectangular grid, right. We have looked at finite difference operators on a regular triangular grid, and I have given you some idea of what the complications might be if the grid is irregular. Okay. So, as we have seen, in order to get these finite difference expressions, finite difference approximations for the difference operators, what we need is the values of the function at many grid points, at several grid points, right. So, now if we do not know, it is possible that we might need to, for instance, if we adaptively refine a mesh, right, if we adaptively refine a grid, that is, we add grid points at locations where of interest, right, where we have sharp gradients or the solution varies very fast and things like that, right. For instance, if we are trying to find out stress concentrations, right, we might want to add grid points at those locations, right. So, if we might not know the function values at those grid points. Suppose we know the function values only at a certain number of grid points, but then as we adaptively refine the grid, we need, in order to we have to know the values at those grid points in order to in order to formulate my finite difference operators, right. So, so in that case we have to find the function values at those new grid points which we just created from my old grid, And how do I find the values, function values at those new grid points? Well, I interpolate, right? I use the values at my old grid points, right, and try to fit a polynomial and then try to interpolate the function values at the new grid points. So that is what we do. So if function values are not known at all the required grid points, it may be necessary to interpolate the function value at one or more grid points from function values at other grid points. In most situations, this is done by approximating the unknown function by a polynomial of a certain order, n say, that is fit through the function values at the grid points where the function is known. The order of the polynomial, the maximum order of the polynomial, depends on the number of grid points at which we know the function values. The polynomial of order n has the form, this is the general form of the polynomial of order n, a n x to the power n, a n minus 1 x n minus 1 and so on and so forth, where this term is known as the leading order term of the polynomial. A n is called the leading coefficient of the polynomial. When a n is not equal to 0, the polynomial is a genuine nth degree polynomial and encompasses polynomials of lower order. Suppose a function f is approximated by a polynomial p n x of order n in the interval a b, right. So we have an interval a b. In that interval I want to approximate a function f of x using that polynomial, that nth order polynomial, and let us assume that the function f is continuous in that interval a b. Define a norm f minus Pn of x in the infinite norm is the norm of the error in the infinite norm. So it tells me how far off my polynomial approximation is from my given function at each point in that interval, right, and I am going to calculate that in the infinite norm. So that is the largest difference over that interval, right. So evaluated pointwise in AB due to the approximation of f by Pnx in AB, right. The theoretical bound of this error for nth order polynomial is going to be denoted as ENF, right. So ENF is a bound on the error. Basically I want to approximate that function fx over that interval AB using a polynomial, and I am of order n, and ENF gives me the smallest value of the maximum error in that. As I use different polynomials, right, I will try to find out what is the maximum error due to that polynomial in that interval. So I fit that polynomial in that interval and I look at each point within that interval, find out what is the error at each point, and then find out the point where the error is the maximum, right, and then I loop over all the set of polynomials of nth order, right. So if I am considering cubic, I look at all the possible cubics, right, and find out which cubic gives me the smallest error, right, the smallest error, right. So it is obtained by varying the polynomial over the set of all nth order polynomials and evaluating pointwise the error using the infinite norm. So what do? I find out fx minus Pnx, the maximum value of this difference over all the points in that interval, and then find out, do this over all the polynomials, all possible polynomials of order n, and when that error is minimum, that is my En of f, right. Is that clear? Okay. So and then there is a theorem which is called the Weierstrass approximation theorem, which states that as n goes to infinity, ENF goes to 0. So what it says that if the order of my polynomial becomes infinitely large, then this error is going to become 0. The error defined like this, right, the error defined like this is going to go to 0. What this means is that, at least theoretically, by increasing the order of polynomials without limit, it is possible to obtain a polynomial of sufficiently high order such that for that polynomial and for polynomials of higher order, the error in this norm becomes 0. Basically the function is the polynomial is exactly equal to the function, because it is the maximum difference between the function and the polynomial value at any point in that interval is 0, right. So, the function becomes exactly the polynomial becomes exactly equal to that function. So, that is what the Weierstrass approximation theorem states. So, when that condition is satisfied, the function f of x is exactly approximated by Pn of x in the interval a to b, and it has been seen that the smoother the function f, the faster the reduction in ENF with polynomial order. So, if my original function is smooth, right, if it has got more derivatives which are continuous up to a sufficiently high order, then it can be approximated, the number of orders we need to go, right, number of higher order polynomials we need to take to exactly approximate that that function is relatively low, right. So, the number, the n, the order of the polynomial we need to use to get ENF sufficiently small, very near 0, is dependent on the smoothness of my original function. It also depends on the size of the interval over which I am trying to approximate f of x. If I am trying to approximate f of x over a very large interval, then I have to take even very high order polynomials. My n has to be much higher. But on the other hand, if I am trying to approximate f of x over a relatively small interval, I can do that with a relatively lower order polynomial. Even a relatively lower order polynomial will give me ENF sufficiently small, right. So, the size of the interval is crucial. The smaller the interval a b, smaller the value of En of f, and faster the reduction of En of f with polynomial size over the interval, right. This means that over a narrow interval, a function may be approximated with considerable accuracy by a relatively lower order polynomial, right. And this has, I want to draw a connection between this result and what we have seen earlier for the Newton-Raphson method. What did we see for the Newton-Raphson method? Well, when we looked at the Newton-Raphson method, we said that near its root, why does the Newton-Raphson method work? Well, I said it works because near its root, any function, any nonlinear function behaves like a quadratic, right. I said it behaves like a quadratic, and since the Newton-Raphson slope exactly matches the slope of a quadratic passing through that point, the Newton-Raphson method converges quadratically near the root of any nonlinear function. So, near the root of a nonlinear function, I said the function behaves like a very similar to a quadratic, and that is why the Newton-Raphson method converges quadratically. Now, here we have a justification for our claim that any function behaves like a quadratic near the root, because in a sufficiently small interval centered around the root, right, that function, my Weierstrass approximation theorem states that function can, smaller the interval, the lower the order of polynomial by which that function can be approximated exactly, right. So, that is why in a sufficiently small interval near the root, E2 of f is approximately equal to 0, right, because as the interval becomes smaller and smaller, I can use lower and lower order of polynomials to approximate the function. So, near the root, E2 of f approximately equal to 0 as per the Weierstrass approximation theorem, and that is why our Newton-Raphson method gives quadratic convergence, right. Any function behaves like a quadratic at sufficiently close to the root. For large intervals a b, on the other hand, En of f decreases so slowly as you increase the order of the polynomial that it becomes infeasible. You cannot approximate a function with only one polynomial in an interval, right. So, if you have a large interval, then even if you use a very high order polynomial, the error ENF is not it does not decrease enough, right. So, we are going to see an example of that. Slightly later on, I am not sure where, yeah. So, So recall also that ENF gives the lower bound of the error over the space of polynomials of order n. Now what this means that in order to find ENF, we have to try all the polynomials of a certain order, right, and we have to find the optimum polynomial, the polynomial which gives me the lowest error in the maximum norm, right, it gives me the lowest error in the maximum norm. That is practically impossible, right. Given a certain interval AB and a polynomial of order n, finding the optimal choice of the polynomial which minimizes ENF is not easy, right. The most common methods of constructing polynomials give errors which are significantly larger than ENF, the error obtained by an optimal choice of polynomial of order n. So if we construct a polynomial, any polynomial, using, we will talk about schemes for constructing polynomials, we construct a polynomial like that, there is very little chance that that polynomial is the optimal polynomial, right. The error it is going to give is not going to be anywhere near, may not be anywhere near the lowest error, for which we have to find out, we have to try all the polynomials of that order and then find the one which gives the lower error, but that is a complex and that extremely expensive process, right. So if the polynomial that is constructed is significantly different from the optimal choice of polynomial, there is no guarantee that just by increasing the order of the polynomial we will be able to reduce the error in the infinite norm to be 0, right. So as just because I increase the order of the polynomial, it does not mean that my ENF is going to be 0. If for that higher order polynomial, that polynomial that I actually use is very different from the optimal polynomial of that order, right. So this is very important, right. Just because I increase the order of the polynomial does not mean that my error, that I am going to get anywhere close to ENF, right, and my error is going to go down substantially, right, because that polynomial may not be the best polynomial, the optimal polynomial of that order, right. That is very important, and that is why the finite element method works, right. The finite element method has something which is known as the best approximation property, right. It is in some sense it is an optimal choice of polynomial. So the choice of it is an optimal choice of approximation, right. The polynomials that we use in the finite element method, they are the optimal polynomials in a certain sense, right. So that is why choosing any higher order polynomial is not going to give me a substantial reduction in error, right. An example of this can be seen if we consider constructing approximation to a relatively simple function f of x is equal to 1 by 1 plus 36x square in a large interval in minus 15 to 15, and by fitting a higher order polynomial through the function values at equally spaced grid points, right. And what we are going to do is we are going to show you, I am going to show you an example of where this function has been approximated by a polynomial of order 10, right, a polynomial of order 10. In order to fit that polynomial of order 10, how many grid points do I need? I need 11 function values at 11 grid points, right, and I fit that function, this red function, right, which is about 1 by 1 plus 36x square over this interval, right, and then I fit it using a 10th order polynomial, right, and what I find, and I use equally spaced grid points, and what I find that near the center of the interval my polynomial approximation is very good, but near the boundaries there are very, very large errors, right, there are very, very large errors. So you can see, even though this is a very high order polynomial and this function is relatively simple, right, it is relatively simple, even then my very high order polynomial with equally spaced grid points does a very poor job near the boundaries. For very high order polynomials, say of order 10, the error in the infinite norm is significantly large. because infinite norm is the error over the entire interval. So, if I look at the infinite norm, it will pick out those large errors at the boundaries, right. So, in the middle portion of the interval the error is small, while near the boundaries the error is very large, right. This is known as Runge's phenomenon, right. This is known as Runge's phenomenon. Thus, choosing the optimal polynomial is crucial to the success of the interpolation scheme and is reason for the focus of interest on specific interpolation. For finite element method is just a special way of picking the polynomials, right. So, it is a special way of picking the polynomials, and that is why we are interested in these special schemes such as the finite element method, because they have these optimality properties which not every polynomial possesses, right, which not every polynomial possesses. Okay. So, now let us talk about some ways of representing polynomials. We will start with the simplest ways of representing polynomials. Polynomial can be represented like this: Pn x is equal to sigma k equal to 0 to n a n x to the power k, or Pn x is equal to sigma k equal to 0 to n a n x minus x 0 to the power k. We can use both these representations to represent the same polynomial. While mathematically these two representations are identical, they may have very important implications if we consider numerical implementation. Why is that? Well, for instance, if the polynomial of interest is in the interval a b, and if the second representation is used, and if we choose x 0 to be the midpoint of the interval a plus b by, which is a plus b by 2, then the accuracy of the computations improve significantly, right. It can be seen, instead of using this approximation, if I use this approximation to represent a function over an interval a b, right, then, and if I choose x 0 to be the midpoint of the interval, the errors due to this approximation are significantly less than due to this approximation, the round off errors. Well, let us look at an example. For instance, if I have a b given like this, right, 50378.796 and this, if the computer stores data, which we looked at right in the beginning of the course, we looked at how the computer stores data, and if the computer stores data in this form, alpha is equal to m times 10 to the power q, with q is an integer, q there is a maximum value of q depending on the computer, and m m is limited to 7 decimal places, say, then a will be represented like this, right. A will be represented because it is m can only take up to, can be represented with 7 decimals, right. So, this will be represented like that, and you can see that the internal computer, the internal representation of these two numbers on the computer is practically identical, right. But the first representation will lead to significant loss of accuracy due to round off. So, minus 0.004. So, this is 0.796, then this is 88. I know what did I do. It should be 800, right, not 880 and 800. So, that is a typo, right. So, in that case, that is going to lead to loss of accuracy of minus 0.004 in A and 0.004 in B, right, since after round off the endpoints of the interval are identical. However, if I use the second representation with x 0 is equal to a plus b by 2, right, so that is my x 0, then in that case this will allow a to be represented by this, because now a is going to be this minus x 0, right, this minus that. So, now a is going to become this and b is going to become this. So, now I have an exact representation, I have not lost any accuracy, right. For the transform variable x minus x 0, these are my endpoints in the interval, right, thus avoiding the loss of accuracy due to round off. So, the way we choose to represent the polynomial is also very important, right, in terms of accuracy. Okay. So, other representations may use a triangle family of polynomials, right. We have higher and higher order, we have polynomials which have bases, right, and those bases form a triangle family. They are of higher and higher order. So it comprises a sequence of polynomials like phi 0, phi 1, phi 2. You can see phi 0 is a 0th order polynomial, phi 1 is a first order polynomial, phi 2 is a second order polynomial, and so on and so forth. Phi n is a nth order polynomial. So these are bases, right, and I can construct any polynomial by taking linear combinations of these basis polynomials, these polynomial bases, right. So aii greater than 0 because I just want to make sure that this polynomial is truly of that order, right. If n were not equal to 0, this won't be an nth order polynomial, it will become a n minus 1th order polynomial. So every polynomial of degree n can then be uniquely represented in terms of these basis polynomials. So those of you who have had some exposure to finite elements, these are very similar to your basis. So these are your basis functions, right, your polynomial. So when we choose first order elements in finite element, we make sure that our basis only involves this and this, right. Higher order elements involve more terms, right, p refinement, right, this we increase the order of the basis polynomials, right. So it's exactly the same idea, right. So every polynomial of degree n can therefore be represented in terms of these basis polynomials. Pnx is equal to c0 phi 0x plus c1 phi 1x plus cn phi nx. The triangle family of polynomials can be used for interpolation as well. Suppose we know m plus 1 grid points x0, x1 through xm and the function values at those grid points. So we can construct a triangle family of polynomials using those grid points, right. So I construct my first polynomial to be equal to 1, right, my second polynomial to be x minus x0, x0 being the first grid point, phi 2 x minus x0 times x minus x1 and so on until I get phi m plus 1, which is x minus x0, x minus 1 up to x minus xm. So using the m plus 1 grid points, I construct phi m plus 1, right, and then I represent a generic mth order polynomial. I know that once I construct my basis functions, right, my basis functions, then I can represent any polynomial of order mth order polynomial using a linear combination of these basis functions which I just constructed, right. So Pm of x, any polynomial of mth order, is equal to c0 plus c1 x minus x0 plus c2 x minus x0 so on plus cm x minus x0 up to x minus xm, right. So the coefficients then I can c0, c1, c through cm can then be uniquely determined from the function values at those grid points, from the known function values at the grid points. Since phi ij x, so this is just I have shown how you determine those function values, right. So you evaluate p of x0 which gives you c0, p of x1 which is going to give you c1 x1 minus x0 plus c0. At x2 you get c2 x2 minus x0 plus x2 minus x1 plus those terms and so on and so forth. So using this, right, we have m plus 1 equations to determine my m plus 1 unknown coefficients c0 through cm, and I can use this to determine my coefficients and fit the polynomial, right. If the actual function f of x for which we are constructing the approximation Pm of x has derivatives that are continuous up to order at least m plus 1, right, that is one order higher than the polynomial I am constructing to approximate that function, then I can write an expression for the error. My function f of x is maybe much higher order. It might be, it need not necessarily be a mth order polynomial, it can be of higher order, right. But the only restriction I am imposing is that the it is continuous up to order m plus 1. If this function is continuous up to order m plus 1, then I can get an expression for the error, right, by approximating the function f of x by this polynomial of mth order. I am going to get an error, right, because the actual function is not an mth order polynomial, right. And then I can get an approximation for the error using and that approximation is given by this value fm plus 1 xi by divided by factorial m plus 1 times x minus x0 x minus x1 through x minus xm. So this is the error due to my approximating f of x with the polynomial Pm of x, right, and this is evaluated at a point. This is equal to fm plus 1, this is the m plus 1th derivative of f, evaluated at a point xi, and the point xi lies within the interval which is spanned, which basically contains all my points x0, x1, xm as well as x, right. For xi is a point in the smallest interval that contains x as well as x0, x1, xm, and is denoted like this. So what I am saying is that I am approximating f of x with this polynomial of order m, and I am guaranteed that the error due to my approximation is going to be given by this term, right. It is going to be given by that term. So by getting some idea of this expression, the value of this term, I can get an idea of the error, right. I can get an so if I know at the point x at which I am approximating my function with this polynomial, I also get an idea of the error involved in that approximation, right. Well, I am going to give a short proof for this. To prove this, we define a new variable z and a new function psi, such that psi of z is equal to z minus x0 times z minus x1 through z minus xm. So I define a new variable z and I define another function psi of z given like this. And I also define another function g of z, which is equal to f of z minus Pm of z, f of z being my original function, Pm being my polynomial approximation, minus r of x times psi of z. So we want to find out r of x such that g of x is equal to 0. When g of x is equal to 0, what does that mean? That means f of x minus Pm of x is given by Rx times psi of x, right. So I want to find out Rx, and psi of x I have already seen is of this form. So psi of x is basically this part, right. I am saying psi of x is like this part, and I want to find out what form must R take in order for me to write this, right, in order for me to write that. So that's how I define g of z is equal to f of z minus Pm of z minus Rx times psi of z, where we want to determine the remainder R of x such that g of x is equal to 0. So at z is equal to x0, x1 through xm, I know that f of z is equal to Pm of z. Why? Because my polynomial satisfies the function values exactly at the points x0, x1 through xm. So at z is equal to x0, x1 through xm, f of z is equal to Pm of z. Also, psi of z is equal to 0 at all those points. At x0, x1, xm, you can see psi of z is going to be, if z is equal to x0, this thing is going to be 0, z is equal to x1, this thing is going to be 0, z is equal to xm, that thing is going to be 0. So psi of z is also going to be 0 at x0, x1 and xm. So since f of z is 0 at x0, x1, xm, Pm of f of z is equal to Pm of f of z is equal to Pm of z at x0, x1 and xm, and psi of z is equal to 0 at x0, x1 and xm. So g of z must be 0 at x0, x1 and xm, right. In addition, since r of x must ensure that we are going to choose r of x such that g of x is equal to 0. So that means that g of z is equal to 0 at z is equal to x as well, right. So from here I know that g of z is equal to 0 at those m plus 1 points. What are those m plus 1 points? x0, x1, x2 up to xm, right. So g of z is equal to 0 at those m plus 1 points. G of z is also 0 at z is equal to x, right. That is because that is how I am going to choose r of x, right. So basically g of z is equal to 0 at m plus 2 points. And what are those m plus 2 points? x0, x1 through xm plus the point x, right. So the function g of z has m plus 2 zeros in the interval x0 through xm. Go back to your first year calculus or wherever you studied calculus, right. A function, if it has 2 zeros, if it has in an interval a b, if it is 0 at 2 points, we know that the derivative of that function, what do we know? The derivative has to be 0 at least at 1 point, right. The derivative has to be 0 at least at one point, at one intermediate point, right. So that's Rolle's theorem, right. From Rolle's theorem, so if a function, so now let us look at this function g of z. So since there are m plus 2 zeros, there are m plus 1 points in the interval where dg of z is equal to 0. If there are 2 zeros, there is 1 point in the interval where the slope has got to be 0. If there are m plus 2 zeros, there are m plus 1 points in the interval where the derivative has to be 0, right. So I know that dgz dz has m plus 1 zeros in that interval, right. Now dg plus 1 dgz dz has m plus 1 zeros. That means d2g dz must have m zeros, right. If you think of this function has m plus 1 zeros, so its derivative must have m zeros, right. Its derivative must have m zeros. Similarly, if we go through this over and over again, it is clear that there must be a point in the interval where d gz dz m plus 1th derivative of that, right, dm plus 1 dz m plus 1 gz must be equal to 0. There must be one point in that interval where this has got to be equal to 0, and let us denote that point as xi, right. Let us denote that point as xi, but we know that the polynomial PMZ is a polynomial of order m, right. So if I take m plus 1th derivative of that polynomial, that is always got to be equal to 0, right. Also, since the leading order term in psi z is z to the power m plus 1, where is psi z? Psi z, right. So if I take m plus 1th derivative of psi z, I am going to get factorial m plus 1, right, because the other terms are going to give me 0, only the leading order term is going to remain, right, and that is going to be equal to factorial m plus 1. So that term is going to be that. Hence, if I go back to my gz and take m plus 1 derivatives, then what do I get? I get fm plus 1z, right. I get fm plus 1z, then pm plus 1z I know is equal to 0, so that term vanishes. I have got rx, and then I have got m plus 1 is the derivative of psi z, which I just saw is equal to factorial m plus 1. So gm plus 1z is equal to fm plus 1z minus rx m plus 1 factorial, and we know that gm plus 1 xi at one point, at some point xi, it is equal to 0. So substituting z is equal to xi in this interval, we get rx must be of that form. If rx is of that form, then g of z is equal to fz minus pmz minus that times psi z, right, and then I replace z by x and I get exactly my expression fx minus px is equal to that, right, which tells me that my error is given by this expression. So, if I have a this should be pm, sorry, f of x minus pm of x minus pm of x is given by that expression, right. So, we have looked at polynomials, the errors due to polynomials, right. We have looked at the Weierstrass approximation theorem, and we have seen on what factors the error depends, right. We have also seen how we go about constructing those polynomials, right, and I also mentioned that constructing the optimal polynomial is really hard, right, but how to construct polynomials in general I have seen. But it turns out that instead of actually, if we have m plus 1 points and we know the function values at those m plus 1 points, we need not really solve that system of equations here, actually solve that huge system, right, for m plus 1 equations and m plus 1 unknowns to find my coefficients. There are simple rules to find out the coefficients. So, if I know m points and if I know the function values at those m points, there are simple rules by which I can construct the coefficients for the polynomials, and that is given by something known as Newton's interpolation formula. We need not solve this system to find those coefficients, and next lecture we are going to talk about that. Thank you.